Okay, so somebody else, we had a question right at the end of class. We're going to get back to this on Wednesday or whenever we come back, about if I throw an object up in the air, goes up, then it stops at the top, v is equal to 0 at the top, and then it comes back down again. All right, and the question was, what is the acceleration at the top? And the answer was that the acceleration is not equal to 0. All right, last name, Jacob? Sanders. So whenever we have stuff that's in the Earth's gravitational field, that when it's near to the Earth or some other planet, the acceleration we say is equal to negative g, and g is just a number. G is the number for, it's actually a measure of the gravitational field. It's not the acceleration, but as far as we're concerned, it's going to be the acceleration due to gravity. So when you have something that's close to the Earth and you drop it, it accelerates at a certain rate. And that acceleration is equal to minus 10 meters per second squared. You'll often see this. You might have had other classes where it's 9.8 meters per second squared. But I just use 10 because it's easier to work with 10, and it doesn't really matter if it's 9.8 or 10 or whatever. So anyway, the number is easier to work with. And so the question came up as to why is the acceleration not equal to 0 at the top? Because the thing stops when it gets to the top. Let's try drawing. We're going to get to this next week. Let's try drawing the velocity versus time graph for this scenario. Now, here at the bottom, I have a big or small velocity when I first throw it up in the air. Do I have a big or small velocity here? I have a big velocity. And is it positive or negative? It's positive. It's going up and it's big. So I'm going to have a point right here. That's for that situation. And then as I go up right there, it's smaller, but it's still positive. All right. So as I go up, it decreases with time. And then when I get up to the top, the velocity is 0. And then as I come back down again, right here, the velocity is now negative, and it's speeding up until finally I get down to the very bottom, and I'm all the way down here, and my velocity is big, but in the opposite direction. Okay, I throw this thing up in the air. It has a really big positive velocity here. It has a smaller speed, but still in the positive direction here. And here, the velocity is 0. So my first part of this graph just has a straight line going there, and then it stops at the top, and then it turns around and starts going in the negative direction, just like that. So my v versus t graph for this scenario looks like that. You're going to do this in lab next week too, but I will give you, that's going to be questions that we'll have. I'll ask you to, pick the graph that describes this scenario, and this is the graph that describes this situation, throwing something up and coming back down again. But remember, when we were drawing plots of graphs, if I had a v versus t graph, the only way to have 0 acceleration on this graph is to have a 0 slope. But notice right here that the slope is not 0. In fact, the slope has a very particular value at that point. What is that value at that point? It's the acceleration. And what's the acceleration? Negative 10. Right, so it's negative 10 meters per second squared. So the slope is not 0 at that point, so the acceleration isn't 0. You can think about it another way. So imagine if I throw this up and it goes up. So here, my velocity is up, my acceleration is down. That causes it to slow down, slow down, slow down, slow down, slow down. Remember, because if my velocity and acceleration are in different directions, then the object's going to have a decreasing speed. It's going to be slowing down. Not if it has a negative acceleration. That's sort of beside the point. It's only if the velocity and acceleration are in opposite directions will it then have a decreasing speed. So here the velocity is up, acceleration is down, slowing down, slowing down, slowing down, stopping, and then it turns around and comes back the other way. And now the acceleration is still negative, negative 10, and then now the velocity is going down. So that means that it's speeding up, but it's speeding up in the negative direction because now the velocity and acceleration are in the same directions. What would happen if I were to throw it up and the acceleration were to be 0? That is, I throw it to the top, and all of a sudden the acceleration goes to 0. What would that physical scenario look like? Right, it would look like that, because the velocity wouldn't be changing, it would just stop. But if the acceleration is always -10, it's going to have decreasing velocity, decreasing speed, and then increasing speed, but in the opposite direction. That's kind of nuanced, but it's really important that you understand that, and then also that you understand how to represent that in a graphical way like this. No way, I said we're going to have a lab about this, and we'll spend more time on it on Wednesday and probably on into Friday practicing this.
So,
yeah.
So with the kinematics equations with acceleration, you can, if it's not given, you can always assume it's -10.
No, so the acceleration is only -10 if you're in the vertical direction. And we haven't really gotten into those questions yet, but we're going to do some today. Let me show you some practice problems. So what I did, any other particular questions? No? All right, you want to look at some tests, some old tests? Let's see, these are all the tests. I like to do sort of the more recent ones, but the old ones are useful too. All right. Let's do a kinematics question. All right, here's one. This is Fall 18, number 13. Fall 18 exam, number 13. You throw a ball up with an initial speed of 60 meters per second. How high does it travel? And so first of all, I know right away that my acceleration is -10. And I just know that because, you know, I'm throwing it up. It's in the vertical direction. And I like to draw a picture. It always helps. If you don't really know where to start on a problem, it always helps to draw a picture. It helps me. I mean, even if I come to a problem and I don't really know where to start, that's just what I do. I draw a picture. It helps me to just sort of think about the scenario that I'm dealing with, and it just helps me to think out loud on the paper. So it's important for you to draw a picture, especially if you're sort of struggling a little bit. All right, so drawing a picture, I write down what I know. So right away I know the acceleration. I also know the initial speed. The initial speed is v0 equal to 60 meters per second. And now I'm looking for the distance y. So I want to know how far does this thing go when it gets up to the top. Now the thing about these free fall problems, these are called free fall because they're objects, the only force acting on them is the gravitational force. I know some other information in free fall problems. And this one in particular, a very important piece of information. What is that? What is the other piece of information that I know about this scenario that will be very helpful in solving it? I know I've written down the initial velocity, the acceleration. I don't know the time. I'm looking for the y position. What's something else that I know about this scenario? Well, what did we say about an object as it's traveling in this type of path? I'm just looking at the first half where it goes from here up to there. What do I know about that object's motion? It's always true. What does the object do when it gets to the top? All right, it stops. So I know that the velocity at the top is equal to 0. Is equal to 0. So I can write that down as well, that the velocity at the top is equal to 0 meters per second. And it's important because the velocity at the top is 0 meters per second, and I also want to know what is the position at the top. So these two things occur at the same time. If I find the time for one of them, then that's going to be the time for the other. The y position that I'm looking for occurs at the same time that the velocity goes to 0. Now, I like to write my equations over here. V equals V0 plus AT. You'll have like a bubble form on your test. I recommend that you just sort of write down the few equations that we'll have on that bubble form, and that way you'll sort of have like your own little equation sheet as you're going through the test. And then y is equal to V0 t plus 1/2 AT squared. So I'm looking for y. The things that I know this. I don't know that. I know this. I don't know that. So if I can just find t, then I can find out what y is. But I don't know t. In order to do that, I'll need to find the time. I can look up here as well. I know this. I know this. I don't know this. I also know this. So I can find the time by solving that first equation. I'll say that v is equal to v naught plus at. V is 0 equals to 60 minus 10 times t. Numbers are really easy with that. What is t going to be? 60 minus what is equal to 0? 60. So t is 6 seconds. Okay, so now that I have that two-step problem, I can find y. Y is equal to v naught, which is 60, times t, which is 6, plus negative 5 times 6 squared. I skipped a little step. I just put in a is equal to negative 10 right here, and half of negative 10 is negative 5. So that's where those numbers came from. And then that gives me, what, 360 minus 5 times 30, 150. No, it's not 5 times 30. 180. The 5 is just half of negative 10. So I skipped a little step here. It's supposed to be 1/2 of negative 10, which is negative 5. That's 1/2 at squared. So it's 360 minus 180. So the answer is 180. I know that seems a little complicated. Like it seems like there are several steps, but we'll do this a bunch in class, and by the time you come to the exam, you'll know free fall problems really well. Free fall problems are really important because on the next exam, we'll have projectile motion, and you'll need to know how to do free fall problems inside and out, like in your sleep. So you'll definitely have a problem that's something like this, where I'm asking you, how long has it been in the air? What is the velocity at particular times? And I said, don't worry, we'll work those in class. Are you worried? You don't look worried. Not worried, right? No. Okay. Let's look at some others. Oh, here's a two-step problem. Number 10 and 11. This is another kinematics problem. So a commuter backs her car out of her garage with an acceleration of 3 meters per second squared. How long does it take her to reach a speed of 4 meters per second? So it's fairly straightforward. In fact, it's a two-step problem, but I with two separate questions, and I just broke it up into two problems. So let's write down what I know. I know that A is equal to 3 meters per second squared. I know that the final speed, V, is 4 meters per second. What else do I know? I know the initial velocity. It's not stated, but it's assumed that she was, stationary inside of her garage. I think that's fairly safe to assume. So I'm looking for how long. I'm looking for the time. So you can probably tell I'm going to say V is equal to V naught plus A times T. I'm going to solve that for T. V minus V naught. I subtract V naught from both sides. Then I divide by A. And so that's 4 minus 0 divided by 3, which is 1.3 seconds, or D. Yeah? Not hard, right? No? What happens if she brakes to a stop in 0.7 seconds? Then what is the magnitude of her deceleration? So I'm starting here with a different problem. I have to write, I know my time is 0.7 seconds. I know that my final velocity is going to be 0 because she's braking to a stop. And I know that my initial velocity is the final velocity up here. I was at 4 meters per second, and now it's like she's slowing down again. So that's going to be 4 meters per second. And I'm looking for A. So I'm using this equation, this kinematics equation again. A is V minus V naught over T. which is going to be 0 minus 4 divided by 0.7. What is that, 5.7 or so? Yeah, 5.7 meters per second squared. And it's not negative because I'm just asking for the magnitude, not for the actual deceleration. Okay? Let's do some graphing problems. I think there was another one on this test. Oh, wait, let's see. Here's another one. So consider the commuter in the previous two problems. While stopping in the 0.7 seconds, what distance does she cover coming to a complete stop? So I would, I'm looking for the distance. This is v naught t plus 1/2 at squared. I know some of these values. I know t is 0.7. I know v naught is was v naught 4 meters per second. And I know the acceleration. I just found that 5.7 meters per second squared. And so I can find the x position she has, or the distance that she covers. That's going to be 4 times 0.7 plus 1/2. This is where you need to be careful. This should be negative 5.7 times 0.7 squared. So that's 2.8 minus something. It has to be 1.4. It can't be any of the others. Because I know that this is 2.8 right here, and I'm subtracting some number. So none of these make sense. It has to be the 1.4. Now listen, on your exam, I don't know when the exam is. Is it next week? Is it on Wednesday? No, it's not on Wednesday. It's not for 2 or 3 weeks. It's probably the week after, like not next week, but the following week. It's on the syllabus. On the exam, what you're going to have, I don't think I started doing this on this exam. Let's see. I don't think so. Oh, good. Y'all in for a treat. So you will have free response questions. So I know that in my 101 exams, I didn't have free response, but I started doing that in the spring semester, and I really liked it. And the students really loved it too. So you're not only going to have multiple choice questions, you'll also have free response. And like, for example, this string of 3 questions all in a row, that would be a good free response question, something like that, where a question where I'm asking you multiple things. You benefit from the free response questions because you can get half credit with the free response. Like even if you get the answer wrong, you can get half credit. I cram 2 or 3 questions into a single question, but it counts like 4 times what a multiple choice question would work. So I take these 3 questions, make them all one question, and then make them worth like 3 or 4 times what a regular question was. You follow what I'm saying? It does have a couple of free response questions, but they'll be worth like 7 or 8 multiple choice questions. It makes the exam a little shorter, but it still gives the same number of points. It benefits you. Like the students did better on the exams after I started doing that, but you have to know how to do it. I'll give you some inclination of what the questions are going to be like. Like I'll say, hey, it's going to be a kinematics question, or it's going to be a vector question, or whatever. I'll give you some preview of what those free response. I'm not going to tell you exactly what it is, but I'll give you a preview of what to expect. But probably it's going to be a kinematics question, something like this, that'll have multiple parts. You can do that, right? Like y'all can probably do this question right now, even just after what we did in class today. But if you can't, that's okay. We have lots of practice coming down the pipe. Okay, questions? All right, let's look at a graphing problem. Because you could also have a graphing problem. Actually, probably what you're going to have is a kinematics and a graphing problem. But again, we'll come back to that. What is this object's acceleration at t equal 1 second? First, you want to recognize what kind of graph this is. This is a v versus t graph. And then I need to remember, okay, v versus t graph. I can get 2 things from a v versus t graph. I can get the acceleration and I can get the distance traveled. I get the acceleration from either the area or the slope. Which is it? It's the slope, right? It's the derivative of the velocity versus time graph. That is the slope. And I get the distance traveled from the area. Remember, that's just like the integral. So I think I actually asked both of those here. Yeah, I do. So if I want to know the acceleration at t equal 1 second, Starting right here, I draw a tangent line, but it's really easy because it's a straight line. It's just the slope of that line. And then I find my slope. It's rise, that's 3, run, that's 4, 0.75. No, not 3 over 4. What is it?
2 over 8, or 3 over 2.
Right, 3 over 2. Thank you. So 3 over 2. Be careful. Like, see the scale is different here than it is here. So I have 3 over 2. And so the answer is going to be rise over run, 1.5. E is the right answer. When I make out your questions, listen to me. You listening? When I make out the test questions, I'll work out the problem and I'll put the right answer as an option most of the time. Not all the time. I always put the right answer. But then I'll go through, because I know the mistakes you make, and I'll make the mistakes and then figure out what answer you get when you make the mistakes that you make. And then I'll put those in. So you have 2 or 3 answers that are just common mistakes. And then sometimes you might just have just a sort of a random answer. So my point is, just because you get an answer does not mean it's right. Okay? So make sure that you know what you're doing. You understand? Okay, good. Now, I want to know what distance does the object travel between t equals 0 and 4 seconds. I'm going to erase this. And to find the distance, I need to find the area. And I'm looking at this area outlined in the blue. Right, that's a square and a triangle. So I will find this area. This one has 2 by 3, so it has an area of 6 meters. And then this is 3, 2. This has an area of 3 meters, 1/2 base times height. So that's going to be 6 plus 3 are 9 meters. That's how you do intervals. And if you ever take, I mean, you won't take numerical analysis. If you're chemistry, you might if you go to graduate school. But that's what they do when you calculate integrals numerically, is that you just add up the bins. You add up, you sort of do length times width, and you find the area of the function. It's really simple, actually. But then you program it in a computer. Okay? Yeah? All right. So you'll see questions like that for sure, where I ask you to numerically interpret a graph. Then you'll also see questions. We did some today. Where I ask you to interpret a graph qualitatively. All right. I know. Let me zoom out a little bit. Can y'all still read that? I want to get both things. So consider the previous position versus time graph. That's this one up here. I'm looking at 19. Which of these statements is true? I love these questions. I love to ask you a question and then I have like 4 options. And some of them are true and some of them aren't. And sometimes more than one are true. So you have to sort of spend all the time thinking about it. The object is slowing down between points A and B. Is that a true statement? Well, if it's slowing down, that means that the slope must be decreasing. So there the slope is like that. And here the slope, it gets shallower and shallower. True statement or no? Number 1. It is, yes, true. So number 1 is true. And look, I can go and get rid of that one. The object is not moving at point C. True or not true? True is right, because if I draw the tangent line, it looks like that. That means that V is equal to 0. That means it's not moving. That's what not moving means. When the velocity or the speed is equal to 0, not moving. So 2 is right. Okay, I can get rid of that one. The object has constant velocity at point D. Is that one true? Look at D right here. Yeah, right, because it's basically a straight line right here. So it has a constant velocity. That means that the acceleration is equal to 0. The velocity is not changing, an unchanging slope. So 3 is true. Okay, so I can't get rid of any of them. And then number 4, the object is moving in the negative direction at point F. Is that true? Yes, because it has a negative slope. That means it has a negative velocity. That means it's moving it has a velocity in the negative direction. Now, I know what you're thinking, because we had a question that was similar but a little bit different. You're thinking, oh, but on the y-axis it's positive. I think that's what you were thinking. But this is a position graph, not a velocity graph. On the question we had this afternoon, or this morning in class, there was a v versus t graph. It had a negative slope, but we said it had a positive velocity. But here we're looking at an x versus t graph. It has a positive position, so it's above the origin of your coordinate system, but it has a negative velocity. That means it's moving down or to the left, whichever. So that means 4 is right, and so E is right. Another thing is, I also like the all are correct or none are correct options. I don't give them that often, but they're still valid options. I know that a lot of faculty just sort of throw them in, all are correct or none are correct, but those are valid options, so don't dismiss them out of hand. Okay? All right. Listen, I'm not trying to prep you for the test, but I want you to sort of understand what the test is going to look like, because the tests are kind of high stakes. That if you bomb the test, it's hard to dig yourself out of that hole. And so that's why I want you to learn the physics, really, but I want you to be able to show me that on the test. And part of that is just sort of knowing how to take tests. It will help you in the future. Y'all with me? Okay, good. Let's look at number 20. We did one like this earlier. What is the sign of the acceleration? Give you just a second to think about it. If you recall how we did this, remember acceleration is positive if the object has it's speeding up if the velocity and acceleration are in the same direction. And it's slowing down if they're in opposite directions. So what do you think about number 20? Consider the motion of the particle described by the following graph. What is the sign of the acceleration? Is this object speeding up or slowing down? Huh? Speeding up. I wish on the test that, like, y'all could run your answers by me and you could just look at my thing like, oh. Would that be useful for you? Yeah. Speeding up or slowing down, what do we decide? Speeding up. I know it's speeding up because the slope is getting bigger. It's more negative, but it's getting steeper. So I have a shallow slope up here, and then here it's steeper. So it's speeding up. And what about the velocity? What is the sign of the velocity? Positive or negative? Negative velocity. So the acceleration is negative. This is like I throw something up and it comes back down again. It's like the second part of that. It's falling down and with a negative acceleration, so it's speeding up. So this graph is the graph of this motion. It starts out with a small negative velocity, and it ends up with a big negative velocity. Can you draw the v versus t graph for this scenario? Let's try it. This could be a free response too. Can we draw the v versus t graph for this? Well, is the velocity initially positive or negative? Negative. Initially negative. Is the velocity initially big or small? It's up here. It's initially small, right? I know that because negative slope, small slope, right here. Negative, small slope. That means my first data point from this position is going to go right here. And then over here, that data point, big and negative. So I can connect those two. And so my v versus t graph is going to be a straight line that's going to look like that. Small negative velocity, big negative velocity. You need to be able to go back and forth between v versus t and x versus t graphs. Look at one and be able to draw the other, or vice versa. And we're going to do it in class some more on Monday or Wednesday or whatever. Just
the VT graphs will always be linear, right?
for us, yeah, the v versus t graph will. That's not entirely true. So these types of graphs will always be linear. Sometimes I might give you a graph that looks like this for v versus t, and I just ask you the distance or the instantaneous acceleration. In fact, let me see. I think I had one in a previous year. No, that's position versus time. No, I can't find a good example, but I could give you a graph that is nonlinear velocity versus time, but I'll probably be doing that to ask you a distance. Let me show you that, by the way. Let's say this graph. Let's say that we do this more in 201. Let's say that I want to know the distance that you travel between 1 and 3 seconds. That's why I would give you not a position, but a velocity versus time. And it just, you have to sort of estimate what the area is under that graph. That's why I would do it. If I wanted to estimate the area under this graph, I would do it sort of by counting the squares. Not counting the squares in the way that you do it, but I would just see how many squares, because I know each of these squares is 5, 1. Each of these squares is equivalent to 5 meters. Because it's 5 meters on the x, or on the y, 5 meters per second on the y, 1 second on the x. And so the area of each little block is 5 meters. You follow what I'm saying? And then I can count the blocks. So that's 5, 10, 15. It's like this one and this one are 20. This one and this one are 25. This one and this one are 30. So like the distance would be approximately 30 meters. You follow what I'm saying? How I did that, I counted up the squares, and where I didn't have a complete square, like right here, I looked for another partial square that would sort of complete it. Like these two, this piece and this piece, if you put them together, that would make a full rectangle.
Yeah, like you try to surface transition time and then ask like how far you travel between those two.
No, I wouldn't do that. I mean, yeah, I might do that. Would that be tricking you? You should know that you can't get the position. Actually, no, you can get the position, how far it's traveled, right? That's really easy, right? Like if I give you a position versus time graph, yeah, this is a good question. Good job. If I give you a position versus time graph and I ask you, you know, how far is this, what's the displacement of this guy? Let's say this is 2 and this is 7 between t equals 0 and 10. What's the displacement between 0 and 10? What is it? Not 7, but 5, right? The displacement, delta x, would be x final minus x initial, which would be 7 minus 2, which is 5. And I just said, well, my final position is 7 right here. My initial position was 2 right there. And so the displacement of that object would be 5 meters. The distance would be a little different. Like you would have to, the distance isn't the same as the displacement. I wouldn't ask you the distance. Okay? I'm not out to trick you. I'm really not. But if you feel tricked, it just means that you don't have a good mastery of the material. That if you know the material, sometimes I miss the questions, but I never feel tricked by them. But sometimes I make mistakes. You understand? But I wrote the questions, so maybe that doesn't really count. All right. Let's do a couple more. Shall go. We'll probably get to vectors. We'll do vectors next week. These are all from chapter 1. Any issues from chapter 1 we want to talk about? No? All right. Give me just one more minute. I'll let you go in a minute. I know that y'all ready to go. But let me show you something. Oh, shoot. I have a new website, so. Yeah, there it is. There we go. So if you look at the old 102 exams, this is the same website as y'all, it's just sort of different. If you look at the old 102 exams, remember I told you you'd have free response. Oh wait, no, that's not it. I'm sorry, I don't have the spring 19 exams up. I'll show them to you later in class. All right, any questions? Are these helpful for you guys? Yeah, it's good. It's sort of a recap of stuff we've done. I'll see you on Wednesday. Y'all have a great week. I think I got everybody. Maybe I got you.